Hello and welcome everyone. I'd like to thank you very much for joining this class on NXP's EV charging software and support. My name is Mark Swinburne and it's going to be my pleasure today to guide you through this presentation. Okay, so let's begin by identifying and then indeed addressing some of those design challenges that are commonly found by our OEMs in EV charging station development. As you can see, clearly from this very busy overview, that electric vehicle charge station developers have got several design challenges that need to be managed. And that can range from new and emerging standards for metering accuracy, like iCorrect, for example, to numerous communication stacks for interfacing to the vehicle and indeed the infrastructure. An example of that could be, for example, OpenADR. And the NXP approach to reduce this burden is using a platform approach where we'll be encompassing and resolving those main design challenges and hopefully reduce the risk, cost, and indeed the time to market. So as I said, the NXP approach is to build a platform, and that's because integration and interoperability is probably where most of the developers' cost, effort, and risk is spent. And we see a platform approach as a very effective mechanism that can enable the developers to streamline and indeed accelerate. So when we pull out the common functionality, it all really fits around the need for integration. And that can be integration in software, so the operating system integrating with the cloud, perhaps there's a file system and indeed graphics and a graphics user interface. Then we want to have a flexible and scalable hardware platform that will allow us to move up and down in performance, but also to add zero-touch cloud onboarding, for example, device provisioning, because there may be a need to give ownership to different stakeholders within the operation of the charge point. Because we have a cloud, then obviously we'd like some form of cloud to device, device to cloud command and control. At the same time, we want to synchronize those devices with things that could be happening either in the environment or indeed in the cloud. That connection needs to be secure. So we want to have something like TLS 1.2 and indeed add to that the opportunity for mutual authentication so that we bring some assurance that we are talking to who we indeed think we're talking to. We can add NFC as a single tap authentication, and that improves the interaction with the customer's experience. And also because now we are able to communicate with the cloud, it would be good to have a dashboard to enable us to visualize that telemetry, that data, but also simplify the control remotely to that device. And because we're in the cloud, then it would obviously open up the additional cloud services and IoT platforms that are available. Okay, so let's map those building blocks onto the EasyEVSE enablement platform. So the purpose of this platform is to enable engineers to very quickly set up that mutually authenticated connection between what is a simulated electric vehicle charger and Microsoft Azure IoT Central EV application. So once we're connected, or once developers are connected, then we can exchange telemetry and indeed commands to manage this behavior of the simulated EVSE. The platform is also able to introduce some of the basic functionality, certainly the JE1772, which is used to manage the state and indeed the low-level signaling between the charging station and the vehicle. And although it is a framework demonstration platform, the idea behind it is once you become familiar with its building blocks and functionality, then a developer could be able to take it on and further develop the platform to support the full EVSE functionality. So let's take a look at the key hardware blocks and indeed its functionality. So at the heart of the system, as I said, it's the main application and the GUI, which is running on the IMX RT1060 or indeed 1064. And that's integrated with the Azure real-time operating system from Microsoft. To that, we've added the SEO50, which is adding edge security and resilience in the form of the SEO50 secure element. And then we have that authenticated connection to Azure IoT Central. and then we're able to offer that device to cloud and cloud to device, both data control and communication. Then we add the meter billing accuracy via our pre-certified Kinetis KM34 metrology device. And then finally, we're adding that one single tap authentication and customer interaction with the CLRC 663, which is an NFC reader design suited for this application. And we're going to use a number of those services within the cloud that we'll talk about shortly. Okay, the main application is driven and accessed via the GUI main screen. And this allows us to interact with the other evaluation boards and indeed with the cloud. And we can then use the Azure IoT application dashboard, which is hosted in the cloud, to visualize and indeed interact with the platform remotely. Okay, the choice of operating system, the framework, and indeed the IDE is fundamental to the enablement and functionality of the platform. And as a result, from the very outset, we wanted to incorporate some of those technical advantages which are offered by Azure RTOS, for example, namely the fact that it's real-time and small footprint. For those of you who are familiar with ThreadX, which is what this is based on as the scheduler, it is one of the truly industrial real-time operating systems that are available. And as such, it's a multi-component, all under one umbrella. And that is simplifying the integration, which was one of our key care abouts at the beginning. So for example, we have ThreadX for the scheduling, we have GUIX for graphics, we have NetX for that secure connection. FileX gives us that resilient file system, and USBX for communication as well, all of which are under one roof and designed to be interoperable and simplify that integration step. What we also get is this pre-certification for a number of safety standards. For us in EV, of particular is IEC 61508, but also can be used in other regions or other markets, for example, medical or automotive. But we also tap into the ThreadX also being, as part of the file system, has EA level 4 plus common criteria and FIPS pre-certification as well. And important for us is the fact that it's complementary when we use it with any of the NXP devices. So that's a real-time operating system. Then from a cloud perspective, we've chosen Azure IoT Central. Fundamentally because it did simplify that cloud connectivity, but as important was having that secure TLS connection, which also supported mutual authentication, which we need. And we're also then able to have that device twin dashboard in the cloud for visualization, and then giving access then to some of the other services that are available for analytics, etc. And then the final piece for us was the choice of IDE. We chose our NXP's MCU Expresso. That's an Eclipse-based software and tools integrated development environment to which we can also add some of NXP's middleware. For example, the IEC 60730 certified library, which is very familiar to those in smart appliance, but also gives us a level of assurance and reliability of the software. And also, again, we can provide this complementary when used with NXP devices. Okay, so from a support and documentation perspective, the evaluation kits that we shared are standard. So we would normally rely on the existing SDK documentation and tools. But for the EasyEVSE specific support, we've covered that in a number of key documents. So the first one is the user guide. Then that user guide has been taken as the source for a getting started video, which will take you through the key steps, including some of the minor hardware modifications, how to get the software, how to install it, how to connect, but that's done in a video in a nice, clean, easy way to follow. Then we have a more in-depth look at each of those building blocks in far more detail via the user manual. The software is available for download, providing you have got your nxp.com account, and it comprises of software for running on the metrology board. We have two versions one for the KM34, one for the KM35. The reason why we've done that is because we don't want access limited by availability of boards. So we felt that having projects for different boards would help getting access to them and beginning the evaluation. We also have for the host, we have a project for the IMX RT1060 and for the RT1064. Same purpose. We don't want to be limited or hindered in any way by the availability of boards. So we chose at least two boards that we can support in the host project. And then finally, the EasyEVSE dashboard, which sits in the cloud, is actually a shareable link that you can import and start using straight away. Okay, so from a code execution perspective, and this is really diving into the user manual, each key aspect of the application, for example, the metrology or the metering, NFC, will also contain a written operational explanation, and that's contained within the user manual. That will further be enhanced using software flow diagrams. And indeed, when you look inside the code, you'll also see that we've included some additional comments, and that really should aid the further explanation and understanding. So let's take a snapshot of the main application. So this is looking inside the user manual. So here we have the operational theory now of the EasyEVSE platform. So at the start, the code first initializes the IMX RT. This can be the 1060 or 1064, for example, and sets up the clock set. It's a very familiar startup procedure. But once that's complete, then we will begin the creation of the various required threads. So we'll be setting up the GUI, the graphics, we'll set up the security, we'll set up the NFC, for example. These threads will then manage the interaction with the user or with the cloud respectively. And then the main application will then provide updates to the meter. So for example, it can send terminate command to the meter, or indeed it could read the latest meter measurement or calculation data. And that data could then be used for transmission to the cloud, but also displaying that data on the user interface as well. Okay, so that's the main application. But as always, from a demo perspective, seeing is indeed believing. So what I'll share with you now is a very high level video of the demo platform in operation. Let's take a look now at how we can utilize the Azure RTOS and IoT Central functionality in our EV charger application. So I'd like to start with the initial connection. So let's assume we've already done DPS and we've been provided with an endpoint in a secure way. The next time the device connects, the idea would be that whilst we use the onboard SEO50 to carry the security credentials, we won't be using DPS now because we want a quicker connection, but no less secure. And what we'll see is the SEO50 being used as part of their key agreement and mutual authentication. So let's start the connection. So we will first start the SEO50 on board, make sure that it's communicating properly. Then we connect, we exchange client hello messages, we create some secrets and exchange them, and then we have a secure connection. So you can see that once the device is registered, we are able to connect very quickly and yet in a mutually authenticated way to the cloud. So now we're actually sending telemetry to the cloud, and we can actually view that in the dashboard that we've prepared for you that you can see on screen. Okay, so let's take a look at the actual demo itself. So if we switch to the car screen, what we can actually see is the vehicle ID and the battery level. Let's change that battery level to 75%. And what we'll do is we will use NFC as a scheme or a mechanism for authenticating the user. So in my hand, I have a MiFi EV1 card that the demo is going to read. So we read the card, it will take the information written on the card and we'll use that to authenticate the user. So you notice now that the vehicle ID, which is the customer, has changed to BBC 64000, and that ID will also get exchanged in the cloud. Okay, so now we're authenticated. What we'd like to do is to commence a charge. So let's switch now to the EV charging screen. So let's go to the screen. At the moment, we're not in a charge. So what we'll do is we will start a charge by moving to state C. So now we are in a charge. That's reflected certainly on the dashboard of the device. That information will get then transmitted to the cloud so that the cloud will follow that action and activity. Okay, just looking at the display, we can see the data matches with the cloud. For example, the grid power limit in the dashboard is showing 16 amps, and the grid limit on the development platform is also showing 16 amps, and they communicate and synchronize with each other as we go through the demonstration. Okay, so let's focus a little bit more now on the IoT application. What we can see, or what we've already seen actually, is telemetry going from the device to the cloud. We can actually control the behavior of that charger. So let's say that it's been a particularly warm and sunny day and there is an abundance of energy in the grid. So the grid operator says actually all the chargers connected can now increase their power limit from 16 amps, let's say up to 32 amps. And as a result, the cost of energy has actually gone down. So let's reduce that unit cost, and that equates to a tariff rate of 0. So now we're going to send that properties information down to the device when we send it. So it will attempt to send it. We'll register that in the device as it gets sent, and that'll get reflected in the dashboard now when we switch back. You'll also notice on the demo that the grid limit has now increased to 32 amps. And then when we go back to the dashboard view, it tells us that our grid power limit is now 32 amps. We can see the tariff cost has gone down to $5 cents, and that equates to tariff rate 0. And depending on the charge, the current that's being drawn by the simulated vehicle, that will affect the power and then obviously the overall cost. And it's counting down as well. Okay, so that is how we use properties to control the behavior. It's also a way of synchronizing across many devices, both at initial connection and actually during its operation. Now at the moment the charger is actually in a charge. What we can actually do is also send a command. The command that we've put together here is the terminate charge. So hopefully when we send the command, it'll be immediately recognized by the device and the charge state will change back to not charging, not connected. So let's run that. So it is first of all detected by the device, and the device should tell the power board to stop the charge, in other words, to change the charge cycle back. And indeed, if you look at the demo itself, you'll see on the screen that charge state has now gone off, and we can actually look at the state has gone back to state A, which is not charging, not connected. Okay, so that's a demonstration then of how we can use commands and how we can use properties to control that. So for the demonstration point of view, we've come to a logical conclusion, and it was really about showing you very quickly how we can, in combination with Azure RTOS functionality and IoT Central application, how we can communicate in a secure and controlled way. Thank you very much. Okay, so let's start looking a little bit more detail or a little bit more closely at the software. So from the project and application file perspective, we've got the showing the contents of the source folder, and of particular interest is using the config or the EVSE config file. That's where we will configure the connection settings and how we choose to authenticate, so the scheme we're going to use, whether it's a shared access key or SAS. Is it an X509 certificate that's going to be stored locally in software within the i.MX RT, or is it going to be using an X509 certificate that's stored inside the SCO50? We'll also have the GUIX, or the graphics main application. So this is where we store all of the resources and behavior of the actual graphics that we interact with. The next file of interest is the IoT file. This is where we have all of our IoT application, which is handling that connection and indeed the MQTT exchange or messaging between the device and the cloud. Very important file for us. Then we have the modified I2C touchscreen driver. It's been modified to include a mutex. That mutex is taking hold of the I2C comms between the TFT controller and the i.MX RT. And the reason why we do that is because when the SEO50 is communicating, we want to give it priority over anything else that might be on the I2C bus. Because the SEO50 is time sensitive to information either that it is asking for or is it indeed expecting. So while we're using mutex, we're able to give it that exclusivity and priority on the bus. Then we've got the main application code, so that's main.c, where we expect some of that initialization to be done. Then from NFC perspective, we have the PH app init.c, and that's where we are setting up the NFC library and indeed initializing some of the polling requirements for the chip. Next, we have the SEO50 specific setup files, which is preparing the device for communication. And then finally, one of the files of interest is the GUIX app. So this is the actual project that gets created when you run the GUIX graphics tool developer. And it's a very nice way to interact with the graphics tool as well as your source code. And very useful to make minor adjustments as well as you go along. Okay, so just a few words about the DPS. So I said that we needed this secure mechanism for registering devices securely during that first connection. And we want to do that without the need for an IT professional. So supporting DPS or device provisioning service is a helper service that we have available to us in IoT Central, and that's enabling that zero touch just in time provisioning provided which is provided to the right IoT Central application without any intervention whatsoever. So it's zero touch. DPS is enabling the provisioning of millions of devices in a secure and scalable manner, which means that when you go from the initial development into production, you won't be inundated with extra manual steps. So we're going to rely on a CA certificate to enable the device certificates, the individual device certificates that have been signed, and we'll register that with Azure IoT Central automatically every time for the first time that device connects, and it'll do that using this device provisioning service, or DPS. So IoT Central does support 3 attestation mechanisms. I mentioned them earlier on, which we're going to use for confirming the device authenticity during that registration step. And that is the X509 certificate. That can be stored inside the SEO50 for best security, but also it can be coded into the software, and we'll show you that later on. We also can use a trusted platform module as well as a symmetric key. And actually, we're going to show you the SAS or symmetric key certainly in the initial startup and setup, because it's probably the easiest way of getting the platform running, although it's not recommended for production as it is not considered as secure. The EV charger platform itself does use 509 certificates as well as SAS. It's completely open to you guys to set yourself in order you want to authenticate your devices connecting to IoT Central. So let's look at how we combine the digital identity and confidentiality, and that's going to be using TLS. TLS is an industry standard, and it does provide identification, authentication, confidentiality, and integrity, whilst you have communication between the device and the cloud, which is perfect for what we need. And every TLS connection begins with a handshake. This is a protocol that is indicating and managing the cipher suite during the negotiation step. The client and server authentication, and indeed the session key in exchange. So it consists of first the hello phase. So here we've got the cloud and the device negotiating the protocol, the version, and the cipher suite. Now the client and server key exchange phase begins, and that's where we're exchanging the certificate. So we'll have the cloud certificate and the device certificate. And those certificates, because they are related to the same CA, then they will be mutually authenticated or mutually confirmed, because they are, as I say, they are related to each other. And then finally, the session secret key calculation phase can begin. And this is where a secret is created and exchanged, which is based on random values. And that will create a unique session key every time you start and begin a secure connection. So it avoids that ability to replay. So very important that we have TLS, which is giving us the security, and we're going to rely on X509 to give us that authentication. So from a provisioning, so this is how do we get those security credentials into the cloud, and then how do we assign them to a unique or individual device. And what we have is many of those manual steps that would be traditionally involved in provisioning of a new device to a cloud or a backend server. We want to automate that with device provisioning service, and that should reduce the time to deploy devices, and it also lowers the risk of manual error as well. So let's look at how it begins. So first of all, the OEM will first of all create the secrets, confidential material, and that will be added to the cloud, so to Azure IoT portal, but also it will be programmed into the device. Now that can be into the flash of the device, or indeed, as recommended by us, into the SEO50 that sits on the evaluation boards. Now the device, when it powers up, it will contact the device provisioning endpoint. The device will then pass the information to DPS to prove its identity. DPS can then validate the identity of this device, and it does that by validating the registration ID and indeed the key against the enrollment list entry that is using the standard X509 verification standard. And if that is successful, then DPS will register this device with the IoT Central application, and it will populate the device's desired twin state for the first time. It will also return the device ID information to DPS, which in turn will send it on to will send this information onto the device. And that means that the device can now start sending data directly to the IoT Central application and not have to go through DPS every time it connects, which speeds up the process. So now the device can connect direct to the IoT Central application, and then the device gets the desired state information from the device twin from IoT Central, so it can now synchronize itself. Okay, so for simplicity, we're going to use SAS for the first connection, which will allow you to become familiar with some of the key requirements, where the software is located, what you can change, and how. So let's begin with a very brief demo of how we implement that SAS key. And today I'd like to show you how simple it is to add a new device to the Azure IoT application. and how to set up a symmetric SAS key for authentication. We'll then use that information to code our project so that we can run our application on our EasyEVSE platform. So let's review the steps first. So first of all, we're going to create and register a device within the Azure IoT application. We'll record those device settings. Thirdly, then we will add those device settings to our EasyEVSE source code. And then fourth, we will run this code. We'll use DPS, the device provisioning service, to provision this device and allow us to obtain the host name for our final step. And then our final step is to indeed add that host name to the EasyEVSE source code so that we can continue with normal operation without DPS. Okay, so let's begin with our first step. So I've prepared a text box which should help us to record the detail and just summarize those steps. Okay, so looking at the NXP's EasyEVSE application, this is running in Azure IoT Central. What we're seeing now is just a view of the dashboards. So the first step for us is to create and register a device. So let's go into devices. So this is now showing us a summary of all the devices that we have registered and provisioned. We're going to go ahead now and create a new device. So let's go ahead and use the add new. Okay, so we have opportunities to enter the device name and the device ID. So for simplicity, I'm going to use the demo EVSE as my first choice. So let's remove the device name. Okay, so we'll have demo EVSE, and then for the ID, we shall have, so let's go demo EVSE device. We don't have to assign a device template at this point, so we won't, but we need to make sure that this is not a simulated device. So let's go ahead and create it. Okay, so now here it is created. You will notice that it is registered, it is not provisioned. So we need to go further steps in order for us to do that, and I'll show you how to do that next. So let's go into our new device that we've just created. And we'll use the connect option, which will give us more details about the device. So we're going to need to record the ID scope. So let's take a copy of that. Okay, we have the device ID, so let's take a copy of that. We need to make sure that the authentication type is selected shared access signature or SAS key. And as a result, we can now record or copy the primary key. So let's take a copy of this. Our primary key. Okay, so now we have all of the credential information that we need. We will then take the next step, which is to add these settings to the code. Okay, so let's go to MCU Expresso, where I have the project open. So let's go to the EVSE underscore config.h, where we will enter all of the new device settings. So let's open that file. Okay, so this is blank at the moment, so we need to populate it with those credentials. So the first one is the device ID. So let's go and get our device ID that we entered earlier on and paste it in here. Okay, next we have the primary key. So let's go and collect that and paste it here. Okay, good. So that's our primary key. As we move down, we get to the option whether or not we want to use DPS or not. And if you recall, I mentioned that we have to use DPS if we want to move any device from registered to provisioned, and it needs to be provisioned to operate. So we need to use the device provisioning service. So we're going to set that to 1. We're going to enable it. And as a result, we have the ID scope, which we did record earlier on. So let's take a copy of that. Paste it in The endpoint is always the same for in DPS. We'll always use the same endpoint, so we don't need to edit that. Okay, so now we've added these settings to the code. Now we'll need to run this code using DPS, and we'll stop execution so that we can actually record the IoT Hub host name. We'll need that, which will then reinsert that into the code next. So let's go ahead and build that and put it into our platform. And let's register the device. Okay, so our source code has compiled and it's in the IMX RT development board, and we're ready to execute. So we've just stopped at main. I've also opened a terminal so that we can watch the debug output from the board as we execute. And let's just check that our new device is still registered, and we want to use DPS to move it from registered to provisioned by authenticating using that SAS primary key. Okay, so let's run our code. Okay, so here we go. So we'll start the connection. Now we're going to use DPS. Remember, we're going to pause it. Okay, let's pause it there. We've paused it because we want to get that host name. So we need to extract that. So let's copy that there. And we'll put it in our handy text file. Good. Okay, so we can carry on execution now. Okay, so now if we go back to the application, we should see, if we refresh, our device is still showing as registered. Let's refresh. And if we've done it correctly and we've authenticated using that primary key, then we move to provisioned. Excellent. Okay, the final step for this, as far as this device is concerned, is to improve the dashboard view. And the way we can actually do that is we can migrate or assign that device to a different template. So let's go and assign it to the EasyEVSE dashboard, which just gives a more pleasing layout for receiving and displaying the data. Okay, so we're registered. Now we need to go back and change the connection type to non-DPS or to, let's say, standard operating mode because it's a lot quicker. So let's go back to our source code. Let's stop it there. We go back into EVSE underscore config.h. Okay, and we will go and disable DPS. So at the moment it's enabled, we're going to disable that. Okay, and then at the same time we're going to replace your host name here with the real host name. So let's copy that. Oh. Okay, good. So again, what we'll do is we'll compile that and program that into our board, and then we'll see the direct connection not using DPS. And if everything is correct, we'll be able to update the telemetry. Okay, so here we are. We've just updated the host name, compiled it, and programmed the new settings into our IMX RT. And the idea now is we're going to do the same connection again, but this time we won't rely on DPS. We will make a direct connection using the host name. Okay, so let's go to the project. Okay, we just started a debug session. Here is our output terminal, so we can watch the connection as it happens. So let's establish the TCP/IP link. Okay, as you can see, much faster this time. We've made the direct connection and we've already exchanged initial telemetry, and now we're in the telemetry update loop. So as you can see, DPS was fundamental in taking a device from registered to provisioned. But once we've done that with DPS, we don't want to use it again because there is a small time penalty for using DPS. So moving to a more direct route, using the actual name of the IoT host is much faster, especially on a line that potentially has issues where you may lose connection intermittently, and then being able to reconnect as quickly as possible. So hopefully that's been very useful, and you now have the confidence and the ability to set up this new device connection and using a SAS key. If you want any more information, then please visit nxp.com. Thank you very much. Okay, so we've now detailed the key building blocks that are available through the EasyEVSE platform. But we should also appreciate that these building blocks are indeed common, and they could easily be repurposed to enable lots of other different applications. So, for example, a connected smart appliance, for example, for example, a washing machine, perhaps, or indeed a secure access control system, but also many, many more. So, when we look at what we have in the EVSE platform, we have the integrated approach, where we had zero touch using DPS. We were showing cloud services where we could visualize the data. We used authentication using X509 or indeed SAS for our first connection. We also have the ability to sync locally with remote. We're able to control it remotely as well as through the GUI locally. And we can bring in security with X509 and indeed NFC and MyFair. So again, many of these building blocks can be simply repurposed and applied to different applications. So for example, if we wanted to apply this now to a connected washing machine, again, pretty much same hardware, same software setup, using many of the same functionalities in the cloud with device provisioning. We may choose to use IoT Plug and Play, which is a very easy and structured way to organize the data that gets exchanged. And then that visualization can be hosted within an IoT Central application. And that application could then give the visibility or access to the OEM. So for the first time, the OEM can be directly connected to the customer for the first time potentially. And that customer can also gain information, whether it's analytical information or information directly from the OEM, or indeed extra products and services. So again, just simply repurposing. Again, using the same building blocks, we could also think about developing or building a building access control system. Again, using the integration of the graphics of the IMX RT with a secure connection to the cloud, with using DPS, for example, for that device provisioning, and then being able to visualize that and control that from the cloud. So again, lots and lots of different applications once you become familiar with the key building blocks. So I guess to finish, for further reading and additional support, for the very latest public updates, for training, any more exciting news, I certainly recommend you visit the EV charging station section, which is available on our nxp.com/energy website. And I would like to thank you all very much for joining this class. I hope it was useful. And if you have any questions, by all means, contact your local NXP representative. So finally, I'd like to thank you once more and have a great day. Bye-bye.